Okay, so it's time, right? I can start? Perfect. Okay, thank you very much for coming to my class. So this is about, oh, all right. It's always the start. This is about Gromov-Witten and Donaldson-Thomas theory. In the title of the course, Donaldson-Thomas theory came first, but it really should come second because it was first. The narrative is that the story is that Gromov-Witten was motivated first, and then Donaldson-Thomas was created beyond Gromov-Witten theory. So I start with Gromov-Witten theory, and then I continue with Donaldson-Thomas theory, tell you why we are interested in counting sheaves, what kind of sheaves are they, and so on. And then course continues with the discussion that counting sheaves turns out to be very difficult, so we need other techniques to actually do that: motivic integration, derived algebraic geometry, and so on, calculations of these invariants. Okay, so just as a reminder, next session is tomorrow, next session, Thursday, here, 9 a.m. to 11 a.m. 9 to 11 a.m. So I'm planning to have this course every. I will need to go back to Boston, where I live, and then nevertheless, the lectures do not stop. The lectures keep going online and so on. Everything is recorded on Zoom, so hopefully you can take advantage of that. Okay. Probably Tuesday also this time, if it works for everybody. I will just keep it Tuesday, Thursdays in the morning, and then Monday, Wednesday, Friday this time. But it really depends on you guys. My point is that you guys come into this classroom, and you should give me permission to teach it whatever time you're comfortable with. I'm kind of at your service. Okay, all right. So let me give you at least the narrative behind it. If you don't know what Gromov-Witten theory is, some of you have had background in physics and string theory and so on, but nevertheless, I give you one intuitive picture, and then we jump right into definitions and so on. So in quantum mechanics, the whole story is about quantum mechanics, in classical mechanics. In classical mechanics, if you have a particle progressing from one state to another state. So for instance, you have a ball and you throw it in the air, or you have some car moving on some path from, let's say, Miami to Chicago. It traverses some path, and you would like to calculate energy of the system. So energy of this mechanical system is certain integral. So you need to have some measure, tells you per unit of length, whatever, with respect to the metric that you design on that ambient space. With respect to that metric, per unit of distance, how much energy you will be spending. So as you integrate this measure over that space, over the path, you will be calculating total energy of that object, going from A to B. So that's classical mechanics. When you do quantum mechanics, it's different. So you have, again, some space, so some state. So in quantum mechanics, of course, there is the actual geometric path that quantum particles travel, but there is also a Hilbert space that parameterizes their state. So every particle comes with a state. So you can think about, I'm in the Hilbert space, and I'm kind of, my state is progressing on some path between all possible states, and this is kind of reflection of the actual geometric path that I'm traversing. So anyway, it doesn't matter. I don't distinguish between the two. So you go from your quantum mechanics, so quantum mechanics. So you go from some state to another state. And again, you would like to calculate energy of the system. The point, though, is that in quantum mechanics, you cannot necessarily tell which paths the particles take. So a particle going from A to B might go from many possible paths. And everything is probabilistic. So there is a probability, so probability P1, so this is a probability, let's say, that your particle can take path number 1. And then there is a probability P2 that your particle can take path number 2. And it keeps going like that. So there is always a chance that your particle takes one of these paths. So this is a mysterious problem, and it's really caused by Heisenberg's uncertainty principle. The remedy to this thing is to integrate energy measure over all possible paths. So this is something that Richard Feynman actually formulated. Feynman path integral. So Feynman said, I'm a quantum particle, I want to go from state A to state B. I might take this path with 10% chance, this path with 20% chance, and so on and so forth. What should I do? Well, I can integrate over all paths. I can write down a weighted sum. 20% chance times energy I have over this path, plus 10% times energy I can calculate over this path, so on and so forth. I add them all and I take an average, probabilistic average. So Feynman is telling you that you do not calculate energy over one path, but calculate expectation value of the energy progressing from state A to B. And why is that the expectation? Because each path you will be taking is the stochastic itself. So that's the remedy of Feynman. So you will be integrating not over one path, but a space of paths. And you will have some measure of energy and some probabilistic measure. I'm not going to write down e to the minus Hamiltonian action and so on, because I know that you have seen these things too in physics. I'm just going to give you the most intuitive kind of possible description as possible, something that an undergraduate student even can make sense of. Because this is what the importance is, that what's the difference between quantum mechanics and classical mechanics. Okay, so that's what Feynman did, and all of quantum field theory is really based on that. And it works really in practice. These allowed people to actually calculate energy of systems of not just even one particle, but quantum particles really interacting with each other. So you have two particles and they are interacting with each other and coming together, and Feynman tells you via his diagrams all possible ways that they can interact with each other. You can calculate energy of the system. Okay, so that's quantum mechanics. Then we come to quantum gravity. So, of course, quantum gravity became an issue, an important topic, because, and I think it started, according to my understanding, it started from Einstein himself. So Einstein was interested in this problem because he was saying, why is it that gravitation doesn't have any whatsoever presence in quantum mechanics? Well, of course, because of the formulation of gravitation is that gravitational force depends on mass of the objects. So if I have this cell phone, I keep it in the air. Of course, between atoms and between the particles that make up the cell phone, there is nuclear forces, electromagnetic forces, and so on. But of course, Earth is also pulling it. But the fact that this object keeps its shape is because the gravity of Earth cannot dismantle them from one another. And why is that? Because the gravity of Earth depends on the mass of Earth and the mass of the atoms in the cell phone. And, well, the way it's formulated, gravity is very weak. But nuclear forces are not like that. The constant that actually gives you the nuclear force between atoms is so large that even though the mass of the particle is very small, still the force is considerable. Einstein was thinking, what if we are in situations where I have a quantum particle in the presence of huge gravitational field, some way that I cannot ignore effect of gravity anymore on quantum forces between them. Where would that happen? For instance, inside the black hole. If I keep this cell phone inside the black hole, of course we are inside the black hole right now. We are sliding through the center of our galaxy. We are inside the black hole. But it's not as scary because we are far from the center. But the closer and closer you get to the very center of the black hole, you will feel this force more and more. When time comes that we're very, very close to the center, effect of gravity on every other system of particles becomes non-negligible. So gravity starts pulling these particles, and they are pulling them too, but gravity can dismantle them because the mass of the black hole is huge. And even though gravity depends on the mass, it becomes non-ignorable. So the mystery was, we have learned everything in the universe, like outside of the black hole. Einstein's general relativity tells us about motion of massive objects in the sky. Inside the atom, quantum mechanics tells us about the motion of tiny objects. But then when tiny objects go to the very center of the black hole, we don't know how to write physics. So the model that describes that is quantum gravity. So it's the mixture of quantum mechanics plus gravitational theory of Einstein, gravitational theory, and it's a dream. It's a dream because we have not achieved formalism of this yet. No one has. And I tell you why. So if you have, now suppose you have particles. Two particles are entangling with each other and they are falling really, really fast towards the center of a black hole, right? And they are progressing from some state A to state B. As they are progressing with each other, so let's say I put 4 particles. So they are coming together and so on, they do some interaction, and they want to separate from each other, and maybe new mass and new energy can be produced. The point is that as soon as you bring gravitational field into this thing and you're integrating over all possible paths, gravity there is very large. And as you know, by Einstein's general relativity, gravity affects the geometry of the space-time. So in quantum gravity, this notion of energy, let's call it quantum gravity, again is an integral. It has a measurement of energy on it, and it has a probabilistic or a stochastic measure on it, and then it also has gravitational metric. So there is some metric, mu of g, that cares about the geometry of the path. And remember that inside the black hole, the space-time continuum will be highly warped and will be highly compactified. So you can imagine that if you have these paths, the possibility of getting really, really ugly paths is very large because of 2 reasons. First of all, the geometry of ambient space is really warped. Second of all, the particles themselves, by their very stochastic nature, they can choose paths which are not smooth. So you could have paths that go intersect themselves like this, and many more such situations. So basically, at some point, the integrand in your integral will diverge off to infinity. You might have paths with singularities. This is a singular point. Or what if your path looks like this? Like that. 1 over x squared, or something like that. So this integrand will diverge off to infinity, and so defining an integral over the space of, still you're integrating over a space of paths, but defining this integral becomes problematic. This integral is ill-defined because there are infinitely many possible paths on which this measure make the whole integral diverge off to infinity. Okay. So essentially, formulating quantum gravity the way it's originally intended is not possible. So there are so many mathematical models created to fix this situation, remedy this situation. String theory is one of this, and the only one that we can talk about, we mathematicians can talk about, is topological string theory. Oh, okay, that's all right. So there are many mathematical models for quantum gravity, and we are going to talk about topological string theory. Topological string theory provides a workable mathematical platform for defining quantum gravity. Otherwise, mathematically, defining such integral is not possible. So what is making topological string theory a workable technology? It is hidden in topology. So in topological string theory, the remedy is that when the particles are progressing from one state to the other, and whenever you get one of these ugly looking paths, you try to smoothen the path. Try to smoothen the path, but keep the topology of the path fixed. So as long as the topological characteristics of the path are kept fixed, you can smoothen it, you can calculate your integral over that path, and you get a nice finite number, but then you need to compensate for something. So you need to, so if you have integral over a singular path of your integrand, you can write that as integral over the smooth path with same topological characteristics plus some term. And that term needs to take into account that singularity of that path. So let's call it correction term. So this is only possible in topological string theory. This is only possible if you actually from the get-go define your integral as if you don't care about the geometry of the path, but you only care about topology. This process that the string theorists use a lot is called renormalization. Renormalization. So in topological string theory, renormalization of paths allows you to calculate Feynman path integral over those paths. Okay, so we are not doing quantum gravity, we are not doing string theory, we are doing mathematical construction motivated by topological string theory. That's the only thing we can talk about. Okay, so that's that. This is the first ingredient. So now you kind of, with this picture, at least I'm hoping that I have motivated why we are not interested in one single path, but in the space of all paths. That comes from Feynman. One. And why we're interested in topology of the path, because that's the only thing we can handle. Okay. All right. Third ingredient. So far, just pictures, right? Nothing rigorous. Third non-rigorous ingredient. In topological string theory, in this formalism, it turns out because of the considerations I really don't want to talk about, plus you can find it in every string theory book, the whole universe is expected to have more dimensions. In order to merge the laws of quantum mechanics, Schrodinger equations, with Einstein's general relativity equation, you need to add parameter to the whole universe. So the most optimal number of dimensions needed in topological string theory is 10. Just turns out that you describe the universe not with x, y, z, t, but with w1, w2, o2, w6, 6 extra variables, then you can merge Schrodinger equation with Einstein's general relativity equations. And you can basically calculate these topological Feynman type path and angles, right? So, okay, 10 is 4 dimensions plus 6 extra dimensions. Okay, so let me show you, again intuitively, something that not experts like you guys or advanced students or postdocs like you guys, but an undergraduate student can make sense of. So this is naively what's happening. So let's say this is my space-time. We have quantum particles interacting with each other and coming together exactly like how Feynman was telling us. So they make these paths, we can integrate over all possible paths and calculate energy of the system. Okay? But now, in topological string theory, we need to really extend the space to extra dimensions. So let's do it. We add 6 additional complementary dimensions. 6 additional dimensions. Okay? So as we do that, everything and anything that we already were working with need to have an extension into additional space. And in particular, our particles need to have an extension. So it is assumed in topological string theory that the pre-image of the particles in a space-time into the ambient additional ambient space with additional 6 dimensions to the ambient 10 dimensions are tiny closed curves, and those are the strings. So the strings are vibrating strands of energy, and they are vibrating with their own certain frequency, and given the frequency, this is how the formalism is anyway, might be a myth, but this is how they decided to formulate it. They're fluctuating with certain frequency, and depending on their frequency, they give you different particles. Muons and gluons and bosons and fermions, everything and anything that so far we know about quantum field theory and is well defined in 4-dimensional spacetime has an extensions into 10 dimension by a string. Okay, so if we want to extend the whole thing into 10 dimensions, our paths need to have an extension. Now you have this closed curve, and they're coming together, and they give you their path. Okay, so they give you these tubular paths. So as you do topological string theory and you want to mimic what Feynman does, the fact that topological string theory needs you to work in 10 dimensions rather tells you that the path on which you're integrating is not going to be a curve anymore, but it's going to be a surface. 2-dimensional surface. And the whole formalism is equipped with metrics. So in topological string theory, the paths, these are called the string world sheets. These are equipped with their own metric, and they are assumed to be Riemann surfaces. Okay, so now you're doing Feynman path integral over the space which parameterizes all possible Riemann surfaces. If the Riemann surface becomes ugly, folds itself and becomes singular, the gravitino that you put in here, the gravitational measure that you put in here will measure that. And whenever the path becomes singular, this thing diverges off to infinity. But because you're doing topological string theory, you're allowed to smoothen that Riemann surface, make it nice, and add a correction term to your integral. And so you do in renormalization. So this is possible by smoothing Riemann surfaces rather. So what would your Feynman path integral look like when you're integrating all of these paths? Remember that in topological string theory, you're only interested in the smoothing paths as long as their topological characteristics do not change. So geometry of the path is not as important as its topology. Okay, so let's just see. How did they formulate it? And how we are going to start the course. So I haven't yet started the course, right? Okay. So how did they formulate it? So we know that we are integrating our integral energy of the system is an integral over all possible paths, integral over all possible string world sheets, i.e. Riemann surfaces, which you obtain when your quantum particles or strings progress from one state to the other, interacting with each other. So you're integrating again your measures, so you have the measure of energy you're integrating over, you have the measure of the metric of the space that you are integrating, so that is the gravitational measure, and then you have the stochastic measure you're integrating, because you're calculating expectation value of this edge. So the way you work this out is, you write this as a sum. You stratify the space that parameterizes all Riemann surfaces based on topological characteristics of these Riemann surfaces. You stratify these things. So you stratify over the space, parameterizing space of smooth Riemann surfaces like this, plus stratifying over Riemann surfaces which could develop singularities. As you remember, the strings are allowed to deform any way they want, and the whole Riemann surface can become very singular. So we need to know exactly how it becomes singular. We need to keep track of that. So nice and smooth. So these are smooth Riemann surfaces. And then they could have singularities develop like this. Okay? All we need to remember is where these singularities develop. So we do some kind of surgery operation on it. We cut this thing. So this, when this Riemann surface gets stretched out, this part of it becomes a tube which is infinite length. Length of it becomes infinity. What we are going to do is we cut it. So we cut it somewhere here. And we remember where we cut it. And we replace it with the cap. And we add a correction term later in here. So all we need to know is in how many places does this Riemann surface develop singular structure. And this is something that we are going to call mark points. So we mark it. So I remember when I was graduate student 15 years ago reading about Gromov-Witten theory and marked points, I was like, what, you just mark a space? What is the point of mark? Why can I mark anywhere I mark in here? It's not that. It's actually under the deformation of the surface, your Riemann surface becomes singular in certain spaces. So marking is kind of imposed on you. But the way we solve the problem is that, okay, let me act like a mathematician. What if I have a Riemann surface and I would like to remember at certain locations of it, I have these markings. And I want to keep track of exactly where these markings are. So it's like I have a kind of a skin or some kind of a stretchy kind of textile, and I stretch it, and then I have these markings, and I want to pin it in this room. So I want to remember exactly when to pin it. And those are the mark points. The mark points remember where exactly, as you embed this Riemann surface in the ambient 6 extra dimensions, where exactly those points are, the coordinates of that. So those are the mark points. So you need to integrate over smooth Riemann surfaces which are not as smooth anymore, but they have markings, plus more exotic Riemann surfaces. We are doing string theory. The strings can do whatever they want. So over the space of Riemann surfaces, which might develop more exotic structure. For instance, they might have a hole. So genus 1. Genus 1 with markings, so on and so forth. Okay? All right. So, first of all, when someone reads this amazing literature, work of this amazing piece of work developed over the, I think, 50 years or more, 100 years maybe, since work of Einstein. First thing that you actually, I remember, first thing when I was a graduate student, I took this string theory class with Rob Lee, former student of Polchinski, one of the famous quantum physicists. And then we were saying, yeah, you calculate the energy of the strings and you get this infinite sum. I was like, energy, infinite sum, what do you mean? It's because of this. There are infinitely many possibilities. So as you calculate the result of this expectation value of the energy, you naturally will get an infinite sum. Because the strings can come together many possible ways. Now, whether or not how ordered terms in this infinite sum are going to be zero, that's something that we can discuss later. But a priori, by construction, you're calculating an infinite sum. Okay? We are doing topological string theory. We are not interested in whether paths like this are kind of different from each other by infinitesimal deformations, because we would like to count them all as one. So in some way, I'm trying to count how many smooth Riemann surfaces with genus 0 I have embedded in my ambient six-dimensional space on which I can integrate. How many genus 0 Riemann surfaces with 3 mark points do I have? How many genus 1 Riemann surfaces with no markings do I have? How many genus 1 Riemann surfaces with 2 markings or 1 markings possible do I have? But I don't care about whether one of them is a little bit bent over and kind of almost the same as the previous one. So as long as they are infinitesimally deformable to each other, I want to count them as one. So we are counting. So we are counting paths up to deformations, infinitesimal deformations. Such that in each summand, topological characteristics of the path are kept fixed. So you start from physics, beautiful story, and then you end up with a counting problem. You end up with classical problem in mathematics. You have a space, 6-dimensional. You have these Riemann surfaces. How many can you count? Up to deformability, but with fixed topological characteristics. This is a well-defined classical problem. And this is the subject of Gromov-Witten theory. These counts are invariant with respect to infinitesimal deformations, and are called Gromov-Witten invariants. Now, when I say deformations, it's a twofold thing, remember. One is that the strings themselves can move in different ways. So Riemann surfaces can themselves, because of the movement of the strings, can deform to each other. One. Second is that imagine, go to the very narrative of the story from the very beginning, the motivation in physics. Imagine that you are quantum particles falling inside a black hole. In the very center of the black hole, there is a massive amount of mass there. There's nuclear explosions, masses transforming to energy and energy to mass. So it's true that overall the mass of the black hole keeps increasing, but over there, mass and energy keep transforming to each other, so mass keeps changing. As it changes, gravity changes because gravity depends on mass by Einstein-Schwarz, a stress momentum tensor, right? So as gravity is changing, the geometry of the ambient space is changing. So not only the paths themselves are changing, this ambient space in which the path is embedded is also fluctuating. So you as a mathematician look at this problem, and here is the problem given to you. I have a space, fix that space. We are going to use algebraic varieties to do that. And I have Riemann surfaces. We would like to work over complex numbers, so we would like to think of algebraic curves, complex dimensional one. And my ambient space algebraic variety is going under some kind of deformation. So we would like to give this ambient space a structure. We give it complex structure, we give it Kähler structure, we take the Kähler form and the complex structure of that ambient space and deform it. As we do that and wiggle it, we would like to count how many of such algebraic curves with topological fixed characteristic I have. And I would like to calculate not any number of it, only the ones which obey these deformations. I don't want my numbers change after my ambient space is deforming. So I'm calculating deformation invariance, not just the simple count, but the deformation. Okay? Think about situations, just as a remark, to give you one example of a deformation invariant, which we could even have in topology. How many points do you see here? 2. If you have the points converging to each other because the ambient space is deforming, and then they become 1, here your number of points in this space is 2, here the number is 1. But if you use algebraic geometry, you can keep track of the multiplicity of the points. As 2 points come together, they give you a point with multiplicity 2. If you count points with multiplicity, here you have count 2 points, and here you have count also 2 points. The algebraic geometry keeps track of the nature of the singularity of this space. That's why it allows you to calculate deformation invariance. Working with functions and polynomials is important because exactly it gives you a rigorous recipe to calculate numbers like this. Okay, so that's the kind of intuitive background behind Gromov-Witten theory. At least now I told you why are we interested in counting algebraic curves in an ambient variety. Any questions? Okay, let us forget about physics. After all, I'm not a physicist, right? This is the things I learned from Wikipedia and YouTube. Yeah? Okay, let's go and talk about rigorous mathematics. So let's just discuss about algebraic curves embedded in ambient algebraic varieties and see how we can count them. Okay. All right, so this is the beginning of the course. Stable algebraic curves. Let's first talk about stable algebraic curves. a connected nodal complex projective curve C. So projective means you can embed it inside an ambient projective space. And if you haven't had, by the way, if you're just a graduate student who just started and so on, I think Miami is one of these powerhouses of geometry and mathematical physics. So I'm assuming that you kind of have knowledge of algebraic geometry and so on. But if you haven't seen it, it's fine. Right? You can just search it. Or you can even look at the book of Harsher while we're going through this course. It's fine. Actually, expose yourself to it and then go through the pressure, and then you will see. You will become a much better algebraic geometer. All right. A connected nodal complex projective curve C is called stable if the group of automorphisms of its automorphisms automorphism of C, which is essentially maps from C to itself such that phi is isomorphism is finite. Remember that we have these string worldsheets, and I'm trying to look at spaces that parameterize the string worldsheets or Riemann surfaces with fixed topological characteristics. So I'm trying to do that. I'm in that part. First, you're studying this base of our integrals, the space of these guys. So, actually, one point of view, another thing, hand wavy. Curves, one-dimensional objects, right? One complex dimensional objects. First, we are going to study the space of just curves themselves. This space we also need to stratify. So I don't want to worry about all possible curves which are automorphic copies of one another. So I'm actually trying to first tell you there is a group that captures automorphisms of the curves, and so I'm going to construct a space that parameterizes curves up to automorphisms. That's the first thing I'm going to do. The point though is that in the picture I drew, everything was embedded inside ambient space of dimension 6, right? Essentially, these will be Calabi-Yau varieties, Calabi-Yau manifolds, and so on. There is a big difference between studying curves and curves which are embedded in an ambient space. Gromov-Witten tells you when you have a curve inside an ambient space, that's a map from a domain one-dimensional object into that ambient space. So Gromov-Witten tells you, look at the ball. And for him, the ball is some kind of commutative ring, spectrum of that commutative ring. Take elements of that spectrum of the commutative ring, send it to space. These are maps. And you take a point, intrinsic, algebraic, abstract object, one zero-dimensional thing. You send it to that space. It becomes a zero-dimensional object inside ambient variety. Now, if you want to define a curve inside that space, again, realize it as a map. Take a one-dimensional object, take each point of that one-dimensional object to that space, it gives you a path there. You want to define a two-dimensional subcomponent of that, take a plane, apply the same functor, send every point of this plane into the ambient space, that becomes maybe a surface like that. Gromov-Witten points of view is, if you want to study space versus subspaces, always study functors from a category of commutative rings into that ambient space. We are studying first just curves themselves and the spaces that parameterizes curve up to automorphisms. Then we go over, well, what if the curve is embedded in an ambient variety? Those are maps. We call them stable maps. So stable curves is just a domain of the stable map. Okay? Layer by layer. So this is, as long as the automorphism group is a finite group, we call it a stable curve. As easy as that is. That's the definition. Okay? All right. Moreover, given P1 to Pn points, distinct smooth points of this curve C, we say that C P1 Pn is stable if the group automorphism of C together with these n smooth points on it, which is given by set of maps from C to itself, isom's, such that when you apply to the points, you get back the points. So it fixes the points of, so this is the, of autos of C fixing all Pi is finite. Again, why are we studying this? Remember the paths, the Riemann surfaces? The string world sheet develops some singular structure. String theory says, I can do surgery operation. If it's this infinite length tube, cut it. Cut it, smoothen it, add a correction term to at the end. But then, nevertheless, the string theory tells you, look at the space that parameterizes all of those Riemann surfaces with these cut caps. The ones whose infinite length you have cut, you smooth it. Those are the location of your mark points. So, you have this room, you would like to stretch something in this room. You fix some locations. There are so many different surfaces that pass through these points. You're interested in space that parameterizes surface passing through these points as long as the location of the points is fixed. So you're looking at all automorphisms of the algebraic curve such that the automorphism group fixes the location of the points. Okay, that's why we're doing this. Fact, let C be a smooth, complex, irreducible projective curve of genus G, then A, so this is fact, for G equal to 0, we have C is isomorphic to projective line. Genus 0 algebraic curve is going to be, smooth algebraic curve is going to be P1 for us, and automorphism of P1 is going to be given by projective general linear group, 2 by 2 projective general linear group over complex numbers, PGL2C. So PGL2C, this is something that often undergraduate students learn. PGL2C is the space of 2 by 2 matrices, like that, and projectivization of the space of 2 by 2 matrices, yeah, which itself is P3. Projectivization of the space of 2 by 2 matrices is P3 because complex number, that's C4. When you projectivize it, you get P3. such that what makes it the projective linear group is determinant is not equal to 0. Yeah. Yes. Okay, so for now, good. You say I have the boundary because the picture I drew. For now, let's forget the boundary. Just the Riemann surface, sphere, no boundary for now. Yeah, but then we will discuss about those things which actually happen to be in the string theory, Riemann surface with boundary. You need to define a space that understands Riemann surface up to automorphisms, up to deformations, and up to profiles as its boundary. So those are extra decorations you add to the space. So those are notions of relative Gromov-Witten invariants, things like that. I want to count how many algebraic curves I can pin through some number of points in this room such that the algebraic curve, i.e. the Riemann surface, has certain boundary as at a divisor or something like that. For now, just the Riemann surface. But you're right. The way I drew the picture gives you that impression. Projective 2 by 2 general linear group, or the 2 general linear group, is the projective linear group. Okay? Now this projective linear group acts on automorphisms, acts on P1, and P1 has 2 homogeneous coordinates, right? So the action of PGL2C on P1 is given by well, A, B, C, D acting on the 2 homogeneous coordinates of P1, which locally give you the coordinates of C, because P1 locally looks like C. C1 is given by AX plus BY and CX plus DY. Okay? And these are the 2 modification of the homogeneous coordinates. So these are the new homogeneous coordinates, which also define P1. But this P1 is isomorphic, this thing is isomorphic to the previous one, and that's a P1. So this is a P1, and that's a P1, and this is the action of PGL2C. Moreover, this action is 3 transitive. That is to say, for 3 points in P1, for P1, P2, P3 points in P1, pairwise, if they are pairwise distinct closed points, there exists a unique element of PGL2C, sending them to the 3 distinguished points of P1, the canonical points of P1, sending them to 0, 1, infinity in P1, respectively. Okay, so we know that. I mean, in complex geometry or complex analysis even, this is one of the first things that we saw. Now this is funny. When you want to do real string theory, I'm not going to talk about this. When you want to do real string theory, okay, turns out that, okay, maybe I should actually say that. So all of mathematics, which is written for topological string theory, which uses algebraic geometry, is works working over ring of commutative variables. So these are commutative varieties, right? The whole Calabi-Yau space, the algebraic curve which is embedded in it, and all of that. Locally, these are defined by polynomials in commutative variables. Okay? The truth, though, is that when you do actual string theory, and when you want to mathematicalize string theory, you need to be careful. Commutative variables that give you these geometric nice objects are actually mathematical realizations of the quantum fields that you actually see in the formalism of a string theory. When the fields are bosonic, meaning they represent massive objects, mathematically they can be realized as commutative variables because the bosonic fields very much act like how commutative variables behave, acting with each other. But when you have fermionic particles, meaning very low mass, high energy, their field algebra is supercommutative. So x times y is not equal to y times x. It's actually equal to minus y times x when fermionic fields interact. When you mathematicalize in full detail the string theory, you need to have a theory where you have a spaces equipped with commutative variables and supercommutative variables. So locally, functions that define those varieties you will get out of those are not polynomial functions, elements of a polynomial ring in commutative variables, but they are functions in mixed variables. So normally, locally, they are functions of, so this is what we are discussing in this course. So this is the underlying ring on which we are discussing our algebraic curves, everything. But that's not the reality. The reality is that it's a ring with n commutative variables, and instead of the coefficients taking values in C, they would take values in some Grassmannian algebra of n supercommutative variables. So essentially, this is a sum of Fi, Gi, where Fi belongs to Grassmannian algebra of m variables, and Gi belong to polynomial algebra of n commutative variables. When you do that, everything in here needs to be supersized. The notion of a Calabi-Yau manifold needs to be a super Calabi-Yau manifold. The notion of an algebraic curve needs to be a super curve. The notion of Gromov-Witten invariant needs to be a super Gromov-Witten invariant. And that formalism was not done, but we have been working on it recently with Xingtan-Yao. So that's a really, really different thing. Why did I think about it? Because I was actually thinking about, because I have papers, we can discuss it at the end of the class. We can go forever. When you look at genus zero algebraic curves, this is where it is. That's it. Automorphisms are given by PGL2C. There are 3 transitive, and you send them to 3 canonical points of P1. When you have a super P1, it's different. You need to even work out what are the automorphisms of a super curve of genus zero. What does that even mean? So those are things that send the underlying commutative part of that genus zero curve to itself, fixing the canonical points, but also the functions which are supported on it needs to be sent to certain other functions compatibly. So Grassmannian part of it needs to also be considered. Okay, so automorphisms of supercurves are basically different. Anyways, we are not doing that. For now, we are just doing bosonic string theory, or Gromov-Witten theory. Okay, so moreover, formulated differently, I want to formulate this automorphism, 3 transitive property of these automorphisms. The PGL2C gets mapped to 3 copies of P1 minus the diagonal. What does this mean? So if I take an element 2 by 2 matrix with non-zero determinant in PGL2C, then via this map, it gets mapped to its action on the 3 canonical points of P1. That's the 0 point action of this 2 by 2 matrix on the 1, the middle of C, up to dilations, the middle of P1, and on the infinity divisor, or infinity point of P1. To the complement of the big diagonal, delta in P1 cubed is an isomorphism. Okay? Why am I trying to send P1? Okay, so this is saying that the automorphisms which are fixing the 3 special points of P1 are also realized as map from PGL2C to P1 cubed minus the diagonal. Why? Because you like to send P1 and send 3 points of P1 to distinguished 3 points of P1. You don't want them to collapse. So you go out of the diagonal, the big diagonal. So this map to the complement of diagonals, so each one of these is a point of P1. Because I have the choice of picking many points, this is a P1, this is a P1, and this is a P1. So P1 cubed, but I would like to send it to locus outside of the diagonal so that I get the 3 distinguished smooth points. Okay, so that's that. Part B is the following so this was for genus 0. For genus 1, for G equal to 1, the curve C, I'm going to call it E, elliptic, right? Elliptic curve. The curve C has a automorphism group, isomorphic to, so the automorphism group like this. So let me actually write it like this instead of isomorphic to. Automorphism of E is going to be isomorphic to E of C. I'm going to tell you what that means. Semi-direct product G. And then for G, one of the finite groups, Z mod 2Z or Z mod 4Z or Z mod 6Z. Cyclic groups of order 2, 4, 6. So this E of C is the normal subgroup. So the normal subgroup E of C, which is a subgroup of automorphism group of the elliptic curve E, acts, they call it simply transitively, i.e. that is for 2 points, P and P prime in the elliptic curve E, closed points. If I pick 2 points, 2 closed points of E, then there exists a unique element of this normal group E of C, sending P to P prime, simply transitively. Okay, so this is automorphism group of genus 0 curves, automorphism group of genus 1 curves, automorphism group of genus 2. Let's talk about that. It keeps going, of course, because our Riemann surfaces develop more and more exotic structure. But this is just for the time being what we are going to do. And the whole point of this is to tell you that we have concrete examples of this thing. I'm going to show you that there are concrete constructions for the spaces, we are going to call them moduli spaces, that parameterize curves with finite automorphism groups. Okay? And then the base of our Feynman type path integral will be these spaces. Okay? Yeah, better not, I don't write it in coordinates. Yes, there is. Just look at Wikipedia, automorphism group of elliptic curve. You can write it in coordinates. Yeah, I didn't write it like this one. You're right. For G bigger than equal to 2, the automorphism group automorphism of C is finite. And this is a result which has been proven. Finite and is proven to be of order at most. There's a very cute little proof of this, but I'm not going to cover it. At most, order at most 84 times G minus 1. This is something that I have seen undergraduate students in Harvard sometimes give a seminar talk about how to compute automorphism group of genus G bigger than equal to 2 is at most 84 times G minus 1. It's a nice little thing. And it's available online, it's very famous or so. Okay. Okay, so this covers all genus. Okay? Okay, so there is hope. There is hope that we can have a space that parameterizes all genus curves with finite automorphisms. And we can hopefully integrate over this space and calculate numbers. Okay. All right, here's a proposition. Okay. Let's C be a nodal connected complex projective curve, and let P1 to Pn in C be distinct smooth points, be distinct smooth points. So later these will be our markings on the Riemann surface. Then the system of the curve together with choice of endpoints on it is a stable if and only if every irreducible component C tilde irreducible in C tilde of the normalization C tilde of C satisfies the following. So C tilde IR has genus 0 and contains at least 3 special points. 3 special points. Okay. So when I say special points here means special points. Here means either marked points or nodes. Either marked points or nodes. I'll draw you a picture so that you can have some idea what this means. Okay? i.e. pre-image of nodes of C in C tilde, you have a curve. Think about these 2 lines, and you could have a deformation process that brings one of these things together, and projection will be a singular variety with a node. Inverse of this deformation will be basically blow up. So this is this normalization procedure. If you start from a curve which is singular, and you have some ugly shape down there, so it has some nodes here and there, and it has some markings, the idea of capturing stability criteria for the curve is that look at the smoothing of this thing. So blow up those singular loci, look at the normalization. And then look at the pre-image of nodes and mark points in the normalized curve. And then capture automorphisms of those and discuss about automorphisms there. Okay? The statement of the theorem is that, you see, this is the most important part of actually Gromov-Witten theory. Gromov-Witten theory, stable curves are curves which have components. So the curve originally is not irreducible. It could be reducible. It says that, for instance, it could be a curve like this. I can draw things in real dimensions, so every P1 in real dimensions looks like a sphere, right? So it could be like this, some donut part, something like this, see, or some other variety attached to it. So these are nodes. And then these irreducible components themselves can, after deformations, can develop these infinite length cylinders, these singularities. So which we are going to cut and replace them with the smooth points, but remember where they are being developed. So this is one of those examples of the Riemann surface, the paths that you will get when you do the Feynman path integral. So this basically says that you have nodes and you have markings. We call either a special point. Either is node or a marking. And then you normalize this thing. So you open it up, you normalize it. And this criteria is the one we are going to use in Gromov-Witten theory. If you normalize it, and if you look at the irreducible components of the normalization, some components are the preimage of things like this up there. Some components are the preimage of the genus 0 things up there. Each one of these components might have marked points. So this is going to basically tell you the whole scenario. If it is a irreducible components with genus 0, what makes it stable? If it is a genus 1 component, what makes it stable? Genus 2 component, what makes it stable? Remember, this theorem, this proposition is important because stability, as I have described, is only having finite automorphisms. It's a recipe. I have a Riemann surface. It's stable if its automorphism group is finite. That's one state. Now, I make it way more sophisticated. It's stable if its components of genus 0 have certain number of mark points, genus 1 components have certain number of mark points, genus 2 components have certain... Okay, so this is a connection between these two things. Looks hard in the beginning, but later it will be much better to work with this more detailed description. because it's very hard to go over every complex curve and calculate what's the automorphism group. Is it finite? Is it not finite? It's very hard to compute that. But by looking at irreducible components, I can tell whether this is stable or not. This is that bridge between the two statements. Okay. All right. So pre-image of the nodes in here. Okay. If it has genus 0, contains at least 3 points, i.e. pre-image of nodes of C in the normalization, or markings pi on C. That's what it is. So if it is genus 0, it needs to have at least the normalization. The genus 0 part of normalization need to have at least 3 special points. That's the statement. Okay, and then if C irreducible has genus 1, it needs to contain at least 1 special point. Interesting. Okay. Finally, C irreducible has genus 2. So genus 2 and higher, we're gonna have finite automorphism groups, right? It's a proof. Undergraduate students were lecturing on that. It's an automorphism group whose order is 84 times G minus 1. It's going to have finite automorphisms anyway. The point we need to be careful is the genus 0 ones and the genus 1. The genus 0 1, not every genus 0 curve has finite automorphisms, but if it has 3 special points, that restricts the automorphism group to be finite. And if it has genus 1, it needs to have at least 1 point on it, 1 special point on it, so that you cannot just randomly and freely map it to itself any way you want. As soon as you need to make sure that this 1 point is fixed, that gives you finitely many possibilities. Okay. All right, so that's that. So how much time? So we can go today until 3 or 2:45, which one? Essentially the course at least needs to be 1 hour and a half. So we start 1:15, 2:45, 2:45 is good? Good? Okay. This is a bad question to ask because the answer is obvious. Okay, sure. So here's the sketch of the proof, because this is important, and I'm not going to talk about finite automorphisms anymore. I'm going to work with this criteria after this. Let me at least show you sketch of it. So by the universal property of the normalization, the property of normalization, an automorphism phi from C to itself of C is equivalent. So equivalent to, oops, where is it? Is equivalent to an auto. So I'm looking at autos of this, and I lift it up, I look at it upstairs. So automorphism of this downstairs is equivalent to an automorphism phi tilde from C tilde to itself, mapping each pair, okay, Q prime I and Q double prime I in C tilde. C tilde of preimages of nodes in C to some other such pair. Nodes and markings. See special points. Okay, some other such pair. In particular, we get a map. We get a group. We get a group morphism. We get a group morphism, automorphism of C, together with n markings on it. Okay, to the symmetric group of components, irreducible components of the normalization C tilde times the symmetric group of Q prime I and Q double prime I from 1 to n. Why? Sending an automorphism of C to permutation group, permutation on the set of components of C tilde, okay, and the set of preimages of nodes. Okay, so when you look at a node, if this is a node, then the normalization will have two branches like that. So if you take a node, then this thing will give you 2 points on the normalization, and you will label these things. So when you look at the automorphism group of the curve downstairs that fixes these points, it communicates with the automorphism group of the normalization upstairs, such that takes the component together with the labelings on it to itself. But then you can change the labels. You can change the components and you can change the labels. There is a group permuting the components, the label of the components, and there's a group that on each component changes the labeling of the nodes that you will get. I can take a preimage of a node and call these to 1, 2 or 2, 1. So there is a permutation on the preimages of the nodes, and there is a permutation on the components too. And the automorphism group of this thing has a lift to the product of these two permutation groups, symmetric groups. Okay? All right. So, all right. Okay, when descending the permutation. So since this permutation group is finite, the group auto CP1 Pn is finite if and only if the kernel of the above group homomorphism is finite. Homomorphism is finite. Okay, there is a group homomorphism from here to here. This whole part is a finite group. This will be finite if the kernel of this group homomorphism is finite. What is the kernel? So only if I can show the kernel is finite, then the automorphism group is finite. Okay, we're almost done with the proof. So, but an element of K, okay, is precisely a collection of autos phi tilde irreducible from C tilde irreducible to itself, okay, of the components of C tilde, which fixes all the special points. Special points, i.e. the points Q prime I and Q double prime I, and the points, the markings, the points PI. QIs are the preimages of the nodes, and the PIs are the preimages of the markings. Okay? Then one can see that the group of autos of C irreducible fixing a number of distinct points of C tilde irreducible is finite if and only if C tilde irreducible is of genus 0 with n bigger than 3. This m is a number of special points or genus 1 with n equal to 1. M, let's call it m, number of special points, let's call it m, because markings I called it n, P1 to Pm. So m bigger than 3 at least, m equal to 1 for genus 1 components, or of genus at least 2. Okay, so because of this, instead of looking at computing with writing down maps, automorphism group of a reducible curve like that downstairs, we can just from now on use this criteria. I look at my curve, I look at the reducible components of its normalization. Genus 0 pieces need to have 3 special points at least. Genus 1 components need to have 1 special point, marking or node doesn't matter. The rest needs to be at least genus 2. If there is some genus 0 piece which doesn't have 3 special points, that has infinite automorphisms, scalings. Think about the sphere that you're scaling its radius any way you want. Now you might ask, I still didn't understand. So you translated the problem into automorphism group of the irreducible components, but you didn't exactly tell me why is irreducible genus 0 should have at least 3 mark points. Why is the genus 1 should at least have one special point? You didn't tell me. There's a proof for that too. This part is basically just telling you, instead of looking at the curve, look at the normalization. On the normalization, this part I left out still. There's a proof to this. Why you need to have 3 points, why you need to have 1 point. Okay? But I think probably you know it, but anyway, maybe next time I can do that. That's it for today.